Welcome to Lecture 1, Astronomy, the Study of the Universe. As you might have expected for the first lecture of a course, in this lecture we'll be talking about a number of terms, introducing concepts, and giving a very high-level overview of the topics that we'll be discovering and discussing throughout the rest of the semester. So with that, let's go ahead and jump in. So if we're going to be defining terms, it makes sense to start off with the first question and the first term. What is astronomy? So chances are when you registered for this course, you had some sense of what astronomy was, and hopefully it's at least some passing interest in it. And if not that, then at least the hope that you could suffer through it, the gen ed, and get what your degree requires of you. But I'm going to assume that you're at least a little bit interested, and if not, I'm going to try to make you interested. And so when I refer to astronomy anyway, and as we use the term throughout the semester, what is it that we mean? And I kind of throw this out there, and I welcome arguments, but I'm going to start off and make the claim that it's the oldest science, in the sense that there are a lot of different scientific disciplines out there now. But a lot of them take specialized equipment, specialized knowledge, and sort of build up over centuries and millennia. Astronomy doesn't take any of that, though we certainly can use that. But you can do astronomy just by walking out after sunset and looking up. And so certainly people have done this from the very beginning of time. And one of the things that we'll talk about in the first week, not in a lot of detail, but we'll kind of do a very quick survey and just kind of make the observation that astronomy has been studied by cultures and civilizations around the world for as long as any records exist. So certainly astronomy has sort of grown continuously from ancient times. And so how we're going to define it is the following. We're going to define astronomy as the study of everything that originates outside the Earth, and this is important, how it interacts. And if that seems like that's a big, very broad definition, you're right. And in particular, this second part, and how it interacts, basically means all of physics. So if you thought that you were, if you were kind of weighing the options when you were registered for this class, and you thought, well, I don't want to take physics because that sounds complicated and there's a lot of stuff there, let me take astronomy instead. Well, the joke's on you, and I say that a little bit tongue-in-cheek. It's not going to be too painful, I don't think. But really, astronomy is a huge field because it's not just about classifying things outside and in the universe, though that is certainly a big part of it. But we also want to, after classifying these things and identifying what is it that's out there, we also want to understand, well, how do those things interact with each other? How does the sun interact with the Earth and with the other planets? How does our solar system interact with neighboring stars or galaxies? And how do the star clusters within our own galaxy interact with one another and with other clusters, for example? And we'll talk about a lot more. But the point is that because there's a whole lot of stuff out there, there's also a whole lot of ways that those things interact. And so the good news is that if you're looking at the possibility of working in the field of astronomy, there's jobs, that there will never run out of problems to solve and things to look into because, it's the study of the whole universe. So anyway, that's a lot of stuff. We're obviously not going to cover all of it this semester. We're going to do a pretty good job, I think, of covering at a high level a lot of different topics. But if nothing else, I hope it whets your appetite, and at least I'll have fun talking about it. So what are we going to cover in this class? Since we can't cover all of the universe and everything that's out there, what is it that we are going to talk about? So roughly speaking, the class is going to be divided into three large segments, okay? And roughly speaking, the first third of the class will be chapters 1 through 6 in the textbook, which will kind of be background information. So I'm tempted to apologize a little bit up front because this class is going to take a little while to really hit the ground running and be, sort of full steam ahead. And that's just because as an introductory astronomy class, there are a lot of concepts and terms and ideas that some of you will already be familiar with and some of you may not. And so it's going to be important to kind of systematically lay the groundwork and make sure that everybody's on the same page and that we understand what it is that we're talking about. And so we're going to talk about concepts like the sky. How do we sort of divide the sky up into sections? How do we talk about what part of the sky we're interested in and what's up there? Then we're going to talk about gravity and orbits because, gravity is sort of it's one of the four fundamental forces of nature, and it's the one that is most obviously impactful in the study of astronomy. We will talk about others, notably the strong nuclear force when it comes to the discussion of how stars work and nuclear fusion, but certainly gravity is sort of obvious in how it, in many of the ways that it manifests itself in the universe, and so it's going to be important to spend a little bit of time on that. And of course, gravity is responsible for things orbiting. So we'll talk about orbits. And then we're going to spend a couple of weeks talking about light and telescopes. And that's important because, and I'll say this a few times, it turns out that almost everything we know about astronomy, we know because of the light that reaches Earth. So, a lot of sciences are rooted in experiments. And experiments do play a role in astronomy, but astronomy tends to be much more observational rather than experimental in nature, because we're interested in things that are so absurdly far away from us that we have no hope of going out there and measuring it and coming back. So we're basically stuck here on Earth, and maybe we can go into orbit around the Earth, and maybe once every a few decades we can send a spacecraft out to go investigate another world. But even that is restricted basically to our solar system. So for this class, we're interested in stars in the universe. That's the title of the course. And we have no prayer of ever going out to a neighboring star. Certainly not in the short term, not for this class. So the question is, well, what knowledge can we extract from the information that just comes to us? And that information is light. And so we're going to need to talk about and study light itself. What are the properties of light? And then how can we capture that light using telescopes? And then how can we extract as much information out of the light that we get as possible? So that's going to be basically the first third of the class. The second third of the class is going to be stars. So we'll start off by talking about our sun, because we know more about it than any other star by virtue of its proximity. And then we're going to sort of broaden our view and step back a little bit and look at all of the other stars in the known universe. And we'll study how they form, how they evolve throughout their life cycle, how they die, and what determines why some stars do one thing and another star does another thing. This is the context in which we'll talk about nuclear fusion, which is it's the process that fuels stars, and so we'll spend it's fewer chapters, but there's a lot of content. There's a lot of good stuff in there. So we'll spend some quality time talking about stars. And then once we understand stars, we'll move on to larger scale structures and spend the rest of the class basically talking about galaxies, cosmology, and the universe. And as we'll discuss, galaxies are just huge collections of stars. So we figured out now how an individual star works. We'll talk about binary star systems, and then we'll sort of go way up, in scale to galaxies, hundreds of billions of stars, and how those collections of stars sort of interact and evolve themselves. And then cosmology is going to be this study of the ultimate fate of the universe. So questions like what originated the universe, or what did the universe look like in its very earliest stages? Think the Big Bang. And then where is the universe going? What is it going to look like in the infinite future? And so very large scale questions. And there, as you may not be surprised to know, there's a whole lot we don't know there. So these are very much, particularly in this last third of the class, there's going to be a lot of modern research that's still being done there. So I'll share with you some of what we do know and some of what we think we know, and then I'll tell you where there are open questions. So while we're here, since I mentioned these particular chapters in the textbook, I've included a link here, and there's also a link on the course syllabus We're using the OpenStax Astronomy textbook for the course. It's free, which is great, and I often expect to get what you pay for, but in this particular case, you get a lot more than you pay for. It actually is a very nice book that's been put together. So there will be readings assigned throughout the semester that will go together very nicely, I think, with the PowerPoint slides and lectures that I'll present here for you, and so I think they'll work well in tandem. So that's a high-level description of what we're going to be doing. So let's go ahead and start doing it. So astronomy is, we've said it covers a lot of stuff. And as a result of covering a whole lot of stuff, astronomy is also concerned with both the very biggest and the very smallest scales in the universe. And when I say scales, I mean lengths. Okay, so let's take a look at how different those distances really are. So this is an image, not a real image. It's hard to get a camera 10 million light years away from the Milky Way, but this is sort of a simulated image of what the Milky Way would look like from 10 million light years away. And we'll define a light year again, but for now, if you're not familiar with the term, it's just the distance light travels in a year. So light travels very quickly, and again, I'll tell you exactly how quickly here in a little bit, but it travels very fast, we know that, and so if you let light travel for 10 million years, that's sort of a distance that's very difficult to comprehend. So this is way, way far away from the Milky Way. And you see some structures in here. You kind of see there's, this is probably the Milky Way, as a matter of fact. It's kind of spirally looking, although you can't really see the spirals very well. But you see there's some stuff and there's a lot of, something out here, but it's very indistinct, right? So what we're going to do now is start zooming in a little bit. But first, I want to point out that if we backed up this far away, this square here is 100 sextillion meters on a side, okay, which is sort of mind-numbing. It's next to impossible to actually wrap your head around how big that is, and it also gets really tiring to write out that many zeros. It's one with 23 zeros here behind it, and so one thing that we'll come back to and we'll talk about in more detail. But scientists use something called scientific notation to represent those numbers in a way that doesn't involve you writing out 0, 0, 0, 0, 0, and so on to nearly infinity. And so 10 to the 23 is how we read this. 10 to the 23 power just means 1 with 23 zeros after it. So it's a huge number. Okay, so this is just sort of a mind-bogglingly large square of field of view. So let's zoom in a little bit. So here we've zoomed in by what I would say is a factor of 10, or an order of magnitude. And as is denoted up here, that just means we're 1/10 as far away now. So instead of being 10, we're 10 million light years away, we're only 1 million light years away. And now you can see so the distance this is 10 to the 23 meters on the side now. And here you see a lot more structure, right? You see, a spiral galaxy, and you can see there's another galaxy out here as well. This is the Milky Way. But you see a few what look like individual stars out here in the sky, but we don't know if they are or not. We'll talk about that more. But certainly we're starting to see some more structure. So let's take another step. So as you come in here, we're now sort of zooming inside the Milky Way, and you can see we're kind of we start to see some additional structure. We see some arms here, and you start to see individual points of light emerge. Okay, so whereas when you were really far out, you just saw some swirls, and you said, I don't, in principle, unless you happen to know coming in, I don't even know what that's made of. What is that? Just a swirl of gas? Are there some stars in there? It's really hard to tell. Here, we're close enough, you start to see some individual stars. And as you zoom in again, now we're only, 10,000 light years away, you see some additional structure. And, I won't belabor the point, but you kind of see that with each step, as you continue to go closer, more and more starts to emerge, though not all at once. Now we're only 10 light years from Earth, okay? And things are starting, it's interesting because first when you started to zoom in, things got, you got more and more cloudiness in the image because there were more and more stars, in that field of view. You saw more of them emerge. You saw more points of light. Now, as you go closer, we're seeing more blackness again because we're starting to zoom in close enough to the Earth that there aren't a whole lot of stars in our immediate, within a few light years of Earth, which as it turns out is good for us, but we'll talk about that more as well. Now you're 1 light year away, and the sun is finally the brightest star in the field of view. Okay, certainly from our vantage point sitting here on Earth, the sun is the brightest star in the sky because it's the only one within 4 light years of us. But as we were zooming in here, there were a whole lot of other stars, right? Now we're finally zoomed in far enough that the sun is the brightest star. It still doesn't look that bright, right? But it's brighter than anything else in this field of view. And as we come in now, we're a mere 1 trillion kilometers. Now we're 100 billion kilometers, and you start to have a sense, at least the way it's presented here, that there's some structure to the solar system. Before, all you could see is the sun. Now you see there are some orbits here. Now, having said that, full disclosure, the Earth and the other planets in the solar system, when they orbit, they don't literally follow colored tracks, right? So as a matter of fact, if you came in here, you would not see, at 100 billion kilometers, you would not see these ellipses here. You might see some reflection of light off some of the larger planets. But as you continue to come in, you get more, you're 10 billion kilometers away. Now you're 100 billion kilometers away, and you've gotten close enough that really it's the inner planets whose orbits are now in the field of view. Now we're coming in on Earth, as you might have expected. We tend to focus on Earth when we get in close because that's us. And now the Earth, if you look at where Earth is in its orbit, this is a random location that we chose for it. But the point is that Earth is really, really small compared to lots of, the universe. Okay. And I could belabor this point. We could spend, another hour just, studying each image, and that's not the point. There are a few more images here, but the point here that I want to make is that the universe is just an enormous place, and where we sit is sort of an unimaginably small fraction of the whole. And so that's and this is important at each level. As you zoom in or as you zoom out, at each level, you see different structures, you see different types of interactions and different types of physics, sometimes playing a major role. And so for me, that's one reason that astronomy is so interesting, is that there's so much complexity in it and so many different phenomena that occur and so many different types of objects that you can study. But it could also be a little overwhelming, particularly if you try to cover it all at once. So we'll go ahead and click through and continue zooming in. Here we get to the Earth. Now we're finally on Earth. And for us in astronomy, this basically ends it now, because if you recall, mercifully, at least astronomy is only the study of things outside the Earth and how they interact. And so at least we don't actually have to study Earth itself. This particular set of images does continue on down. I'm going to click quickly through the next few, but I will stop at one point in a few slides for reasons that will become clear. So if you were a biologist, you're getting interested now because we're zooming in on things, on the surface of living things, and you start to see, we don't quite see the cell structure here yet. We will in a minute, but we're not biologists, so I'm going to continue. Okay, so here's where I am going to pause for a second, because now we've zoomed in so far. We started 10 billion light years away, and now we are looking at a single carbon atom. And fortunately, from my vantage point, possibly unfortunate for you, I don't think so. But this becomes interesting to us in the context of astronomy again, because as it turns out, we actually are going to have to be concerned with the properties of and the behavior of individual atoms and even nuclei, because, as I mentioned a few minutes ago, they power the stars. And so here we're at a carbon atom. As we zoom in, we see, you don't really see because its electrons are really spread out, but we'll keep going in. So we have empty space between the inner shell electrons and the nucleus. And now we're starting to view the nucleus of the carbon atom itself. And you'll notice, if you've been following down here, now we're at 10 to the minus 14 meters, also known as 10 femtometers. That means 0.0, 13 zeros, and a 1. So we started off sort of unimaginably large. We've now zoomed in to something almost unimaginably small, and we see this carbon nucleus. And later in the semester, we will talk in detail about nuclear fusion, and the carbon nucleus will actually play an important role in some processes of nuclear fusion, particularly in high mass stars, though it's not normally carbon we're going to be focusing on specifically. And now we come into a single proton, and protons we will be very much concerned with, because a proton nucleus a proton is also known as a hydrogen nucleus. And as you may know, hydrogen makes up the majority of the universe. It certainly makes up the majority of stars, and it's hydrogen that is responsible for fusion in the sun, for example. And so we'll spend quite a lot of time talking about hydrogen and the nuclear processes by which energy is released through nuclear fusion, which powers the stars. And then, because it powers the stars, it powers planets as well, at least Earth. So that's kind of the largest scales to the smallest scales, and everything in between. And so, kind of as advertised, there's a huge amount of content, a huge amount of material that we could study. We won't be doing all of it. We'll hit some highlights along the way, and hopefully, we'll enjoy ourselves a little bit as we do. So, I mentioned this at the beginning, and we kind of saw it in action as we went from the largest to the smallest scales there. But the length scales in astronomy are much more extreme than we're used to on Earth. If you think about the lengths and the distances that we deal with on a day-to-day basis, we deal with things, on our desks, say, that are inches or centimeters to feet or meters. When we get in the car and we drive somewhere, we deal in miles or kilometers, right? If you take a really long road trip, you might go several hundred miles in a day, okay? But that's basically the extent, that's the longest distance that we tend to deal with on an everyday, basis. In contrast, the nearest star is 40 lots of zeros away. Okay, so this is 40 quadrillion meters away, and more than that. Okay, so I keep using the word unimaginable, but it really is next to impossible to wrap your mind around how far that is and how big that number is. And on the other end of the spectrum, we just got done zooming in on the surface of a proton, if you will. Well, those are critical to understanding nuclear fusion and sort of how stars work. But the size of a proton is 10 to the minus 15 meters. 0 with 14 zeros and a 1. And so, in order to understand astronomy, what we're saying is that we need to understand both the very largest things in the universe and the very smallest things in the universe. And if that isn't mind-numbing enough, just as a concept, we're actually going to have to be a little bit detail-oriented. And we're going to, at least occasionally, have to write down numbers that relate to these distances. And so we have to express these tiny numbers and these huge numbers somehow in a way that doesn't overwhelm our paper and overwhelm our, our PowerPoint slides and everything else. And so fortunately, we're not the first people to run into this problem. And the answer to that is something that's known as scientific notation. So you may have run into scientific notation before in a chemistry class or a physics class. If you have, great. If you haven't, well, we'll introduce it here. It's we're not going to use, and I'll try to allay your fears and stress this, a few times throughout probably today and going forward. This is not a heavy mathematically, it's not a heavy mathematical class. Okay, so we're not going to be crunching a lot of numbers. We're not going to be memorizing or deriving lots of equations. As much fun as it would be if we would, I would love that. I love that kind of thing, but that's not what we're going to do. But nonetheless, we will have to write down some numbers, and there will be a few equations that it's going to be important to at least be familiar with and understand their importance in the context of astronomy. So this is not, this is basically just what I said. It's not a class in advanced mathematics, but we will have to write some numbers down. And so we'll go ahead and start right now and just define scientific notation. So scientific notation is a way of compactly writing numbers in terms of what's known as a base and an exponent. Okay? And so, for example, a proton radius is 0 point, lots of zeros, and then a 1. And so we get tired of writing that. And so we write 1 times 10 to the minus 15 meters. And that just means that we had to move, if you look at the number as it's written here, that means we have to take this decimal and move it 15 spaces to the right in order to get the 1, some non-zero number to the left of the decimal. And we'll see some examples, so I won't belabor the point here. Similarly, if you take the distance to Alpha Centauri, which, as it turns out, is a triple star system that is our nearest neighbor stars other than the Sun, it's a little over 40 quadrillion miles, as I said, 40 with quite a few zeros, another 15 zeros behind it. And so we write that as 4 times 10 to the 16 meters, which just means that if we have an invisible decimal, if you will, at the right of this number, because you could always write 0.0 without changing the number. So the question is, well, how many spaces do you have to move that decimal in order to get it next to this 4, so that the number that's left out in front is between 1 and 10. And so that becomes then 4 times 10 to the 16 meters. So and so the base is the number out in front, would be 1 in the case of the proton radius, or 4 in the case of Alpha Centauri's distance. And the exponent is the number that's, that you're raising 10 to. So we'll see more examples, but fortunately scientific notation is something that is extremely common in scientific fields. And so I'll have some links for you as well if you're interested. But if you want to brush up on scientific notation, there are lots of resources online that are very good. And so that's not something to worry about. So to convert a number from standard notation, which is the way that you and I would write normal numbers, if you will, if they weren't so big or so small, you just move the decimal left or right until you have a number between 1 and 10. So that's it. And as you're doing it, you count how many times, you keep track of how many times you had to move that decimal. So the number you obtain at the end of all of those decimal movements is known as the base. So it will always be between 1 and 10. That's just how we define scientific notation. You move that decimal until you get a number between 1 and 10, and that's the base. And then the number of spaces you move the decimal is the exponent. So a little bit simpler example than the huge and the really small numbers we saw on the last slide. If we start with 34,000, we ask, there's a hidden decimal here. So, and this is important to remember, if you have just an integer, a whole number that doesn't have a decimal in it, well, you could always write 0.0, right? So there's a hidden decimal right here at the end of the number. So the question is, well, how many places do you have to move that in order to transform this number or convert it into something between 1 and 10? And so we move it once, and that gives us 340. We move it twice, that gives us 34. And we move it a third time, and that gives us a number of 3.4, which is between 1 and 10. And so that's our base. And then we ask ourselves, well, how many spaces did I have to move that number, or move that decimal? And the answer is 3, and so that's our exponent. And so the scientific notation expression for 3,400 or 3,400 is just 3.4 times 10 to the third power. And that positive exponent means that you move the decimal to the left. Okay, 10 to the 3 is a compact way of writing 1,000. Okay, so we're just saying that 3,400 is equal to 3.4 times 1,000. Similarly, if we start with 0.034, we have to move the decimal to the right, right? And so if we move it one space to the right, we have 0.34. And if we move it a second time to the right, we have 3.4. So we stop then because 3.4 is again between 1 and 10. And then we write down 3.4 times 10 to the minus 2, or the negative 2. And that negative exponent means that you had to move the decimal to the right. Okay. So that's it. That's scientific notation. And again, if you have questions about that, there are lots of resources, some of which I have linked in the course resources, and then others you can just find by Googling, or if you have any questions, you can certainly ask me, and we'll do what we need to do. So I won't actually play this. I told you there were more resources, and lo and behold, here we are. I won't play this video here in the lecture, but it's embedded in the lecture slides, and these are available, as you know, on the course website. So you can certainly watch this at your leisure. It's a great video. I think it very effectively sort of reviews and introduces scientific notation from the Khan Academy, which, for those if any of you are not familiar with the Khan Academy, I certainly recommend their videos and resources for any topic that you're trying to gain a solid introduction to. Okay, so now astronomical sizes and scientific notation. So now that we know how to write these huge numbers and these very small numbers in some sort of a compact notation that, where we won't spend our whole lives writing out zeros, let's start actually investigating a little bit about the length scales, the distances that we're actually going to be concerned with in this class. So number one number that we're going to hit over and over again is the distance between the Earth and the Sun, and that happens to be 149 billion meters, or 149 million kilometers. Also happens to be 93 million miles. I only throw that out because while the vast majority of the time in this class we're going to be dealing either in metric or standard SI units like meters and kilometers, we will, and certainly light years and parsecs, which we'll introduce later, which are sort of astronomy specific terms. The distance between the Earth and the Sun is often quoted in miles, and it's 93 million miles. So that's worth remembering. But the distance between the Earth and the Sun is 149 billion meters, and the size of a hydrogen atom is this. I won't read that off to you in words, but it's lots of zeros and then 5, 3. So if we convert this to scientific notation, we can write this as 1.49 times 10 to the 11 meters, because again, we would need to move the decimal 3, 6, 9, 10, 11 spaces to the left. in order to get a number between 1 and 10. And similarly for the hydrogen atom, we would need to move the decimal 11 spaces to the right. And so we would write the size of a hydrogen atom as 5.3 times 10 to the minus 11 meters. So more examples, but these are actually numbers that we will use from time to time, or at least refer to again throughout the course. So we did a little bit of placing the Earth in context already when we kind of started off, out 10 billion light years and then slowly zoomed in. So we won't do that again, mercifully, but one thing that I do want to do is provide a little bit of context for where the Earth is, like what structures the Earth exists in astronomically, and how we're going to classify them. And these aren't choices that we just made arbitrarily. This is just this is how astronomers classify these things, so it's important for us to be aware of them. So I suspect you know that the Earth is part of a solar system, and we happen to be the third planet from the sun. And so we've got the sun, and then we've got Mercury, Venus, and then Earth is there. As you zoom out a lot, it turns out, the solar system is part of the Milky Way galaxy. And we'll talk about galaxies in much more detail later in the semester. Right now, we're just focusing on the classification, but we live in the Milky Way galaxy. Now, if you zoom out even farther, it turns out that there is a group of between 30 and 50 galaxies, which it kind of depends on how you define a galaxy. Some people will say that something is a galaxy, whereas others will say, well, no, that's a dwarf galaxy, not really a galaxy. It's kind of reminiscent of the discussion about whether Pluto is a planet or not. Turns out even professional astronomers have disagreements over these things. So the precise number of galaxies in the local group is not so important. What is important is that as you zoom out farther, you find that there are other galaxies than the Milky Way, but there are between 30 and 50 of them that are relatively close to one another in some sense, and importantly, they gravitationally attract one another. And so they tend to pull on each other, they tend to orbit each other. And so just as planets orbit in the solar system, these galaxies in the local group tend to orbit around one another to some extent. And then as you zoom out even more, you find that there are lots of different local groups that are gravitationally attracted to one another as well. And we are part of something known as the Laniakea supercluster, which is, as these things quickly become, mind-bogglingly large. And we'll talk more about that in detail. But the point here again, and this is similar to the point I made earlier, is that at each level, every time that you zoom out or zoom in, you see some new structure. And in the early going, one of our goals is to classify those structures and just give them names and labels so that we can talk about them and refer to them as we go on. So, but as we've already seen a number of examples, it's hard to sort of wrap your mind around statements like the solar system is 1.5 times 10 to the 13 meters across. As a physicist or an astronomer, it's easy enough to write that down. It's even easy enough to make the measurement and to believe it once you've made it. But to really internalize it and understand that is something else. So the question is, well, how do we begin to even give ourselves a hope of visualizing these numbers? So one way is to try to compare, when possible, these astronomical things to more familiar objects. So for example, if we're interested in the moon, it turns out that the diameter of the moon is roughly similar to the size of the continental United States. So in this particular image, you can see that the diameter would take you basically from New York City to Ogden, Utah. So that gives you some sense of, now of course the moon is a sphere, so we just plopped it down on top of that. On top of the United States. So if you actually set it on the Earth, it'd be kind of awkward, but it gives you some sense of the diameter of the moon there. Similarly, the distance between the Earth and the moon is about 100 times the size of the moon. And so and that's kind of over here at left, you see this is the Earth and the Moon. And so essentially you could string 100 moons together side by side, and if you did, that would reach from where the Moon actually orbits the Earth to the Earth. So that just gives you, that's one way of sort of comparing these astronomical distances to something that's a little more familiar. And one way that we often express these mathematically is in a quantity known as a ratio. This is probably a term that you've heard of. It's all it means is that you've divided two things. So a ratio just means you've divided things. And so in this particular case, you say S is a variable that's very often used for distance. And so, it might not be obvious that S is a good letter for that, but it is. So SE-M here just means the distance between the Earth and the Moon, and then D sub Moon, or where the subscript is Moon, just means the diameter of the Moon. So if you divide the distance between the Earth and the Moon by the diameter of the Moon, you get about 100. Okay. So that's what we've said before. The distance between the Earth and the Moon is about 100 times the diameter of the Moon. Another comparison of a similar nature is that the Sun is roughly 100 times wider than the Earth. So, in other words, if you took the Earth and you put them side to side, you could string about 100 Earths across the diameter of the Sun. And if you want to be a little more precise, it's much closer to 109 times wider. So that's a useful thing to know. So now that we've compared some distances, the diameter of the Sun to the Earth, the diameter of the Moon to the continental United States, let's compare some volumes. So now moving from one dimension to 3 dimensions. And the question that I'd like to ponder in that context is, how many Earths can we fit inside the Sun? So if you imagine the Sun being this big empty ball, and you're putting marbles into this ball, that represent the Earth. The question is, how many marbles, how many Earths can you fit inside the Sun? So let's pause for a second and think, well, before we just start calculating, what should our approach be? So some initial thoughts. We've already said that the Sun's diameter is 100 times greater than the Earth's. So you can string 100 Earths across the diameter of the Sun. Now, to answer the question that I posed here, we're not interested in distances directly. We're really interested in volumes. We're asking, how does the volume of the Sun compare to the volume of the Earth? Okay, because that's going to be the answer to the question, how many of Earth can you put inside the Sun? Well, both the Sun and the Earth are approximately spherical. They aren't perfect spheres for reasons that we can talk about if you're interested, but they're very close to spheres. And so for these purposes, we're going to assume that they're both spheres. So we know the difference between their diameters, right? We know this factor of 100. Sun is 100 times greater in diameter than the Earth. We know that both the Sun and the Earth are spheres, and we know that we need to compare their volumes. So the only remaining question is, do we know the volume of a sphere? Well, I don't know whether we all know it off the top of our heads, but we have all known it at some point in our lives, back when we took geometry. And so to jog your memory, if you didn't have it right on the tip of your tongue, the volume of a sphere is 4/3 pi r cubed, where r is the radius of the sphere. So if you tell me the radius of a sphere, I plug into this equation, 4/3 pi r cubed, and out pops the volume. And so we have all the information we need now. We just have to crunch some numbers. And so I told you this is not a class in advanced mathematics. There will be a little bit of math now and then, and I'm going to do an example for you here. So we've said that both the Sun and the Earth are spheres. A sphere has a volume of 4/3 pi r cubed. And so we can immediately write down the following equations. So the Sun's volume, which I denote V sub S, not very creatively for the volume of the Sun, is equal to 4/3 pi times r cubed, but the r is the sun's radius, right? We're going to be interested, there are two different radii here. There's the Earth's radius and the sun's radius. The volume of the sun is going to be 4/3 pi times the sun's radius cubed. Similarly, the Earth's volume is going to be 4/3 pi times the Earth's radius cubed. Okay. And now, since we want to know how many Earths we can fit inside the sun, mathematically, what we're asking is, what is the ratio of the sun's volume to the Earth's volume? Or in other words, if you divide the sun's volume by the Earth's volume, what do you get? So, and this is just, it's algebra. We're dividing 4/3 pi r sun cubed by 4/3 pi r Earth cubed. The 4/3 cancel, the pi's cancel, and we're just left with the radius of the sun divided by the radius of the Earth cubed to the third power. And we've said that the sun is about 100 times, the sun's radius is about 100 times larger than the Earth's radius. Full disclosure, what we actually said is that the sun's radius or diameter was 100 times larger than the Earth's diameter, but a radius is just half a diameter, and so the ratio of their radii is also 100. So we end up with 100 cubed, which, if it's been a while since you cubed things, that just means 100 times 100 times 100, and that gives you exactly 1,000,000. And so the take-home message here is that roughly 1,000,000 Earths could fit inside the sun. So it would take 100 to string it. You could string 100 Earths across the sort of the diameter of the sun, but if you want to fill up the sun with Earths, it's going to take 1,000,000 of them. So the sun is a lot bigger than the Earth. So let's do another example. And in particular, let's consider the question, how does the distance traveled by Jupiter in one of its orbits compare to the distance traveled by Earth in one of its orbits? How many times farther does Jupiter travel when it orbits the sun? So first, some initial thoughts. It turns out, and you wouldn't know this off the top of your head, at least I assume you wouldn't, but the radius of Jupiter's orbit is very nearly 5 times that of Earth's. So Jupiter is approximately 5 times farther away from the sun than is the Earth. Second thing is that we need to compare the circumferences of these orbits that Jupiter and Earth are traveling in, right? That's the question. The question is, how many times farther does Jupiter travel than the Earth? So it's the circumference of this orbit, that's the relevant distance. And finally, the orbits of Jupiter and Earth are approximately circular. Now, it is important. We're going to talk in some detail in the coming weeks about the fact that orbits are, in fact, not strictly circular. They're actually elliptical. But it turns out that the elliptical orbits of the Earth and Jupiter are very, very nearly circular. And so to a very good approximation, we can just assume that they are circular, and the error will be very small. So for this calculation, we're going to assume that both Jupiter and Earth's orbits are circular. And finally, the last bit of information we're going to need is that the circumference of a circle is related to the radius through this equation that you've seen at some point in your life, if only in high school geometry, but the circumference is equal to 2 pi r, where r is the radius of the circle. So we know how to calculate circumferences from radii. We know that Jupiter's radius is 5 times larger than the Earth, its orbital radius, and so we're again ready to crunch some more numbers. So we start off just by writing down the circumference of Jupiter's orbit is equal to 2 pi times its orbital radius, and we write down that the circumference of the Earth's orbit is equal to 2 pi times its radius. And next, since the question that's posed here is how much farther does Jupiter travel, what we're asking is, what is Jupiter's circumference divided by, or the circumference of Jupiter's orbit divided by the circumference of Earth's orbit? And so we just have 2 pi times Jupiter's radius divided by 2 pi times Earth's radius, or the radii of the orbits. The 2 pi's cancel. we're left with just the ratio of the orbital radii, and we've stipulated at the beginning that that number is 5. And so this may not come as a shock to you. It turns out that since Jupiter is 5 times as far away as the Earth, Jupiter travels 5 times farther than the Earth does in a single orbit. So that answer may not come as a shock to you, but now you know for sure. So I have commented a couple of times that this is not going to be an advanced math class, and I don't want to scare you off because we really will not be doing very much math in this class. In fact, you've probably seen more math in the last 10 minutes than you will see the rest of the semester. I will have to write down some numbers periodically. I will, on occasion, do a calculation for you like I just did, you know, as way of example. But when it comes to homework and quizzes and tests, you will not be expected to be crunching, you know, large numbers. You will not be even expected to do anything like I just did. I do hope, and you will be expected to remember certain facts, like the diameter of the sun is roughly 100 times the diameter of the Earth, and you can fit 1 million Earths inside the sun. Those are kind of useful numbers to have for the reasons that we've been discussing for comparing one astronomical size to another. But we will not be doing a lot of heavy-duty math in this class. So if you like math, though, and you want more, shoot me an email. I'm happy to oblige. There are plenty of opportunities. And certainly, if you were, this is an introductory, Gen Ed level astronomy course. But if you like astronomy and you want to continue taking astronomy, then the more astronomy you take, as with a lot of different sciences, the more math is involved. And so if you want to be a professional astronomer, you're going to need to be pretty comfortable with math. If you're going to want to get a good grade in Astronomy 20, that's not required. So we talked about ratios a little bit now and comparing numbers. Another way to visualize astronomical objects and try to get some sense of sort of what these huge distances are is to use, and how they relate to one another, is to use scale models. So, for example, when I've taught in astronomy lab, one of the things that I'll often do in the first week of lab is actually take the class outside and walk off scaled distances from, between different planets and in the solar system. And what you'll find out, very often is, well, if you're paying attention, you always find out that the solar system and space in general is a lot of emptiness. There's a whole lot of nothing with a few things kind of interspersed there. And so scale models at least help us to understand, even if the absolute sizes of things still are just beyond our comprehension, they do give us a better sense of relative sizes and distances. And so they can kind of at least help us form a picture of where are stars in relation to one another, where are the planets in relation to one another, how do the galaxies interact, and at least we can form a mental image, even if it's not perfect. So let's look at a couple of examples, involving scale models. So let's imagine if we shrink the sun to the size of an apple, okay, how far away is the nearest star? I mentioned the nearest star. The name is Proxima Centauri. It's one of the 3 stars in the Alpha Centauri system. Not too many decades ago, we thought Alpha Centauri was just the nearest star. But then as our telescopes got better, we discovered that there were actually multiple stars very close to one another. And so Proxima Centauri is the one that is currently closest to us. How far away would that be if the sun were the size of an apple? And the answer is about 2,000 miles, so which is pretty nearly the distance between San Francisco and Chicago. And so if the sun were the size of an apple, the next nearest star is sort of in Chicago if that apple is in San Francisco. So that's a long way away. If we took the sun, and it's an apple, Chicago is pretty far away. So a lot of empty space. Similarly, what happens if we shrink the whole Milky Way galaxy? So now, instead of just the sun, you've got 100 billion stars. You shrink all of that and the space in between them down to an apple. how far away is the nearest galaxy? And it turns out it's much, much closer now, 3 yards, okay? And if that seems counterintuitive, it doesn't need to. But you've scaled things way down, right? So you've taken the whole Milky Way and made it the size of an apple now. But what we found is that the nearest galaxy now is only 3 yards away. So let's consider the question then, which are more likely to collide? 2 galaxies or 2 stars? And I'll pause for a minute to let you ponder that before I give you the answer. And of course, if you want more time to ponder, you can always just pause me and wait until you're ready. But I'm ready now, so I'll go ahead and give away the answer. The answer is that 2 galaxies are far more likely to collide than 2 stars. And the way to understand that is that, if 2 things are 3 yards apart, it's much easier for them to hit than if things are 2,000 miles apart. Okay. So galaxies can and do slam into one another, and we have seen examples of that. We certainly run computer simulations of that. We've seen the aftermath of that in telescopes, but it's very rare. As far as I know, we have never actually observed the collision of 2 stars actually combining. Except, I should say, there are famously now quite a few observations of black hole mergers and or neutron star black hole mergers. Strictly speaking, those are not stars anymore; those are dead stars. And there's a lot of interesting physics and astronomy in those too, and we will touch on that much later near the end of the class. But that's not really relevant here. So let's continue on. So what happens now? We've talked about shrinking the sun down to the size of an apple. What happens if we shrink the sun down to the size of a grain of sand? Just for fun. Well, there are a few things that'll happen. So the Earth then would be the size of a bacterium, and it would be located 1 centimeter away from the sun. Okay. So you don't think of a centimeter as being very big, but remember the sun is now the size of a grain of sand. So, we've scaled things way down. Pluto, which is 1/6 of the Earth's size, is therefore 1/6 the size of a bacterium, and it's located 40 centimeters away from the sun. So Pluto is 40 times farther from the sun than is the Earth. The nearest star, again, Proxima Centauri, the nearest, other than the sun, obviously, is 2 miles away. So, imagine, again, the sun is a grain of sand, the nearest star is 2 miles away. Okay, that's a lot of empty space. All right, and we keep coming back to that, but that's just, there's a lot of emptiness. And the Milky Way galaxy is 50,000 miles across, which is a quarter of the distance to the moon. So you shrunk the sun down to a grain of sand, but you're still 50,000 miles across for the whole Milky Way. And to kind of imagine in this scale model again, what our galaxy would look like, you would have 100 billion grains of sand, which represent the 100 billion stars in the galaxy, and they would each be separated by 2 miles, and they would fill the empty space between the Earth and the moon. So again, a lot of empty space, but some pretty amazing stuff where it's not empty. And to top it off, the nearest galaxy is 1.5 million miles away. It's interesting because we start off, we talked about these scale models because we recognize that it's just it's next to impossible to wrap our minds around the actual distances relevant to the universe. But I have to say, there are ways in which this helps, but I have to say that for me, at some point, when you make the sun the size of a grain of sand, and now you talk about filling the space between the Earth and the moon with 100 billion grains of sand, You know, I find myself a little challenged to sort of actually visualize that as well. But again, I think the take home is that there's a whole lot of emptiness, a whole lot of space between things out there. But then, as I said, some pretty remarkable things when you do find something out there in that emptiness. So we're going to wrap up here. We just have a few slides here at the end where I want to just touch briefly on the concept of the scientific method in general. So this is something that you've probably been introduced to a handful of times in your life, in school at least. Maybe once in elementary school, maybe again a couple of times in middle school, and then, you know, if you took, presumably you took some science class or other in high school, and so you've probably seen this, but it's worth kind of putting in an introductory lecture, putting out here, just because it will kind of frame the approach that astronomers have used historically, and that we're going to follow as we kind of, you know, do our survey of the universe, you know, over the next several weeks. So there are lots of different sciences out there, right? You know, as a physicist, we are, you know, as I am, we are very often tempted to just say, well, there's one science that's physics, and everything else is sort of, you know, on the back burner. But the reality is there are lots of different disciplines, right? And I could name lots, but I won't. And there are lots of specific methods in each, right? There are techniques that are relevant to experimental physics, that are not used in biochemistry, that are not used in sort of physical chemistry, and so on. Lots of different specific techniques and methods, but all sciences have a common general framework and general approach to analyzing nature and trying to make sense of it. Because that's what science is. Science is an attempt to classify and understand nature. And so we call that high-level common approach to scientific problem solving, not very creatively, the scientific method. So, and that scientific method can be, you know, is outlined basically in this schematic. So the idea is that it all starts with an observation or an idea. And so it may be that you are, you know, you're a very early ancient astronomer, and you can't sleep, and so you spent a lot of time staring up at the night sky, and after a while you notice certain repeating motions or common behaviors of the stars. And so you say, well, that's interesting. I observed this, okay? And then you start to think, well, why could that be? Or even if you don't ask the why question, you might say, well, given what I've observed over the last 5 years, I think that next month, that reddish dot in the sky will be right there, okay? And so, and that's a hypothesis. You know, fancy Greek-derived word for a guess. And so you say, well, based upon the observations or the idea or the theory that I've developed, I think this will be true. And so you make the hypothesis, you use that to make a prediction, and then you perform a test or an experiment, or you observe something. And so first you've gotten the data, you've made these observations, you've kind of brought it all together and said, well, I think I understand something about how this is working. If I'm right, this prediction will be true. And then you go and you test that prediction. So it can be an experiment. You know, if you're doing a traditional science, you know, say chemistry or physics, you would do an experiment and say, did the experiment match your prediction or not? And if it does, so if the test provides evidence to support your hypothesis, then you go back and say, okay, well, that's great. You pat yourself on the back, but you make another guess and you test it. And you just keep doing this until you find a test that fails. Okay, your prediction is not borne out. You have this great theory. The first 100 times that you tested it, it worked perfectly. But the 101st time you tested it, it didn't work. Your prediction was not validated. So then that says to you, well, either you took bad data, you were wrong, so you should do it again before you throw away everything. But once you're convinced that your theory really has a flaw in it, then you have to go back and suggest, you have to modify your theory. You have to suggest a new hypothesis. And then after you develop this new theory, Probably not from scratch, by the way. Probably if you've gotten 100 predictions right, there's something to your theory. But you modify it in some way in order to account for this new piece of information that you have, and then you make a new prediction. And if you've correctly improved your theory, then you'll start getting things right again, getting more things right. But science is always in a process of evolving and improving, at least ideally. That's the goal. And so we have, obviously, science has been around for a long time. Some science is longer than others. We've made a whole lot of progress. And in physics and astronomy, we have some very good theories that describe correctly a whole lot of our observations. But as we will talk about, particularly in the last third of the class, there certainly are some areas where there's a lot that we still don't know, and where the theories that people have come up with to date to explain the observations in a lot of cases seem so bizarre that it leaves you wondering, what's really going on. So something to look forward to as we move towards the end of the semester. But this is kind of the ever sort of ever moving scientific method where you're just constantly testing, refining, and hopefully improving things. So the one other thing that I want to throw out at the beginning of the semester, because this is going to sort of undergird everything that we're going to talk about, not just for us this semester in astronomy, but this is really a fundamental assumption inherent in almost all of physics, astronomy, and science in general, which is known as the cosmological principle. And that can be stated a few different ways, but the way that I'll state it here is that the laws of physics are the same on Earth as they are anywhere in the universe. And moreover, those laws of physics are and always have been the same, and they don't change with time. Okay. There's a lot changing in the universe. Planets orbiting, stars exploding, new stars forming, and an infinite number of other things. But the laws of physics, which govern all of those interactions, we assume, we take that those laws are not changing. Okay. We believe this is true as scientists. There's a lot of that assumption has been borne out in a lot of cases. And what it means is, if it's true, that means that we can use experiments on Earth, for example, or the observations of nearby moons, planets, and galaxies to draw conclusions about the rest of the universe. We'll see a great example of this in the context of Newton's law of gravitation in a couple of weeks, where Newton looked at the orbits of planets, developed a theory of gravity which would explain those observations, and then went on to conclude that this gravitational force that he understood to be responsible for the solar system's dynamics is the same gravitational force that's responsible for orbits of galaxies around other galaxies, or about movements around black holes on the other end of the galaxy or of the universe, and so on. And so that's a very powerful thing that we can do, make local observations or even tabletop experiments in the laboratory, and then use our discoveries to determine physical laws, which we can then apply everywhere else in the universe. Okay. This is an assumption, though. It's not a blind assumption. It seems to have worked very well for us, but there's no way to prove that this is absolutely and always true. Okay. And if it were not true, then lots of science would fall apart. So if it's not true, then we're kind of stuck in a lot of ways. But fortunately, it seems to be true, and we haven't seen a counterexample yet. But it's important to put out there that this is an assumption that underlines all of the science that we're talking about. And so there are people that look for violations of this, and that think about, well, what would happen if this weren't true? But throughout the course, we're going to assume this is true, and there's a lot of good reason to do that. So that brings us to the end of lecture number 1. I leave you with a link here. I didn't embed this because it wouldn't embed very well. But I mentioned it several times today that there's a lot of emptiness in space, and there's a pretty cool website here that if you follow the link will sort of demonstrate that in a pretty powerful way with a few jokes along the way. So if you have trouble sleeping, or if you're just you got 5 minutes to kind of click through and look at the page, I would encourage you to do that. So with that, I will leave you. Hope you enjoy the introduction as much as one can, and I will look forward to seeing you again for part 2.